You have probably heard that light can behave both like a wave and a particle, right? It bends around corners and interferes with itself, just like water waves, but it also comes in discrete packets of energy called photons. Now, imagine if something you always thought of as a tiny little ball could do the exact same thing. Could something as small as an electron also behave like a wave? Yes, electrons absolutely do create diffraction patterns, and this fascinating phenomenon is one of the clearest pieces of evidence for the wave-like nature of matter. It is a cornerstone of quantum mechanics, showing that subatomic particles are not just tiny, hard spheres, but also have properties we typically associate with waves. The core reason for this behavior lies in what is called wave-particle duality. In the quantum world, particles like electrons do not just exist as point-like objects. Instead, they also possess a characteristic wavelength, often referred to as their de Broglie wavelength. This wavelength is inversely proportional to their momentum, meaning faster or more massive electrons have shorter wavelengths, while slower or less massive ones have longer, more pronounced wavelengths. When electrons encounter an obstacle with dimensions comparable to their de Broglie wavelength, like the atomic spacing in a crystal lattice, they diffract and interfere, much like light waves passing through a grating. This interaction creates the distinctive pattern of bright and dark fringes on a detector screen. Observing this wave behavior typically involves directing a beam of electrons through a very thin material, such as a crystal or a specialized double slit. As the electrons pass through, they spread out and interfere with each other. If you place a screen or detector behind the material, you will see a series of concentric rings or lines, which are the signature of a diffraction pattern, rather than just a single spot you would expect from pure particles. This concept was first proposed by Louis de Broglie in 1924 and experimentally confirmed by the Davison-Germer experiment in 1927. It was also independently observed by G.P. Thomson, solidifying our understanding that electrons are not just miniature billiard balls. This wave-like property is not just a theoretical curiosity, it is incredibly useful. It is the fundamental principle behind powerful tools like electron microscopes, which use the very short wavelengths of electrons to image structures far too small to be seen with visible light. Understanding that electrons possess both particle and wave characteristics is crucial for truly grasping the quantum world. This duality allows us to explain not only how electrons produce diffraction patterns, but also underpins much of modern technology, from microchips to advanced scientific instruments. It reminds us that at the smallest scales, reality is far more wondrous and complex than our everyday intuition suggests.